Now, when a neuron sends a message, its electrical charge changes a lot very quickly. So before I get into how those particles move when that happens and the gates opening and closing and when that happens, I want us to just look at the charge, whether it gets more negative, more positive inside the cell. So remember, the inside of the cell is negative at rest. This negative charge is called resting potential. In our picture here, we have this flat line for the first few milliseconds. It is showing voltage on the x-axis. We're looking at time in milliseconds. Resting potential is this flat line at negative 70 millivolts. Now, not all neurons have this as their resting potential, but let's just say this neuron we're measuring, the inside of it, the charge is a negative 70. Now, there are a few different ways we could mess up this resting potential. Before we talk about how that happens naturally when a cell receives information from another cell, let's first talk about it as if we, as the researchers, were sticking an electrode in there and making the environment a little more positive or a little more negative. Now, when we have voltage anywhere that is other than zero, if it's real positive or real negative, either way, it's called polarized. The inside of the cell is polarized. It is negatively polarized because it's far from zero and it's negative. We could pump even more negative energy in there. We could make it hyperpolarized. So what we would see is the voltage dip down from our resting potential. And we have an example of that here that happens in a natural situation, and we will explain why later. But this is what a hyperpolarization looks like on the graph. A hyperpolarization actually makes it harder for a neuron to send a message. It actually makes it less likely that it will send an action potential or its electrical signal on to a next neuron. It's going to be inhibited for a little while. We could do the opposite though. We could pump a little bit of positive energy in there and bring up the voltage some so that it goes more towards positive territory. If it's moving from this way negative up towards zero direction, we call that depolarization. It is becoming less extreme. It's going towards the middle or towards that zero. And we're seeing small depolarizations here for these failed initiations. If we put just very small amounts of positive voltage in here, the cell still will not do anything and not send a message. The cell has a threshold, which for this one is negative 55 millivolts. If we depolarize it to negative 60, negative 65, anything like that, it's not going to hit threshold. If we depolarize it so that it climbs up to negative 55 or higher, then it will send an action potential. It is an all or nothing event. It's like not having pulled a trigger or pulling a trigger. It is like pressing the handle on a toilet to flush it or either not flush it. There's not an in between here. We can't have little action potentials or bigger action potentials. We have either a neuron sending an electrical message all the way down its neuron to communicate to another neuron, or it doesn't send anything to other neurons. So in a natural environment, if this neuron through its dendrites is receiving chemicals that get released from other neurons, those chemicals will either depolarize or hyperpolarize part of our neuron, the inside of our neuron. So it could receive a certain chemical that would give it a hyperpolarization. Its inside of its cell will become even more negative, and it's not going to pass a message on to its neighbor because of that. We could receive a certain chemical to our cell that would cause it to be depolarized, which would mean that it would become a little more likely to fire an action potential. It's going to be a little less negative on that inside of the cell. But if it doesn't get depolarized enough, it's not going to send its message either. If it gets a big enough depolarization, maybe from getting a message from multiple cells at one time, or frequent messages from the same cell, it will send an electrical signal all the way down that axon, all the way to its own terminal buttons, which will then release a chemical to communicate with the next neuron. So when that happens, once we hit threshold, we've been depolarized enough, the voltage keeps climbing. And it climbs so high, so quickly, that it's not even negative anymore. Our polarization has now reversed. The inside of our cell is at positive 40. This is the peak of action potential. And notice this has only happened within 2 milliseconds. That's 2 thousandths of a second. Extremely quick electrical impulse. Once it hits this peak, the cell has had enough. It will not get any more positive than this. So it begins the falling phase, in which we have our polarity moving back to the negative territory. But it overshoots. It goes so negative that it goes to like negative 100. And then eventually it climbs back up to resting potential. So the different phases we have are resting potential, getting depolarized to threshold. That threshold depolarization causes the rising phase. We rise until we reach the peak. Then our voltage falls back into the negative territory again, but it goes so negative, it does what we call an undershoot, a hyperpolarization, and then it climbs back up to resting potential, where it will start right here all over again, ready for a new action potential if it receives a new message from another neighboring neuron. We talked about how certain particles inside and outside the cell make it negative on the inside and positive on the outside to begin with. And we talked about channels being closed. So now I want us to learn what the particles are doing at every point. When we're positive, when we're up here at the peak, for example, what particles are inside and which ones are outside now? And we'll see that for the undershoot, and then going back to resting potential as well. Just to orient us really quickly at what we are looking at, on the left panel, we have these green potassium ions inside the negative cell, like they normally are at resting potential. That's our before picture. And we have our sodiums on the outside, and sodium channels are closed. Once we get depolarized to threshold, the voltage comes up to negative 55 or higher. Then the sodium channel opens. And remember, the sodium had two forces of nature operating on it, telling it to rush into the cell as soon as there's a chance. So now that there's an opportunity, that's what we see in the after picture. Sodium channel is open and sodium rushes in. Now we have a ton of sodium inside, even more than we have potassium. So at that point, we've had all these positive particles rush inside, and that makes the inside of our cell really positive. That's what we saw during the rising phase and the peak. So now, after we sent our message, we have this problem where in order to have the cell ready at resting potential to send a message, we need to kick sodium back out and have potassium inside and have the voltage negative inside the membrane again. So we're going to look at in detail that voltage graph again with another one of these particle diagrams next to it to examine what happens at every step on that voltage graph.